Today's topic of the day is randomization tests. Oh, you know what? I did not upload this lecture to CCLE. Hang on, let me pause this. So it is having a lock on the car can be inconvenient when you lose your keys. That's true, but otherwise I appreciate having. Okay, anyway, MFA. I'm a fan. All right, randomization test. This is what we're going to talk about today. And so we will do a concept review of hypothesis tests first, okay? So randomization tests are the computational kind of alternative to using the central limit theorem. But we have to, maybe we should review intro stats and hypothesis testing. I know a lot of you took stats 10, a lot of you did not take stats 10 and you took something that was deemed an equivalent in high school or prior to coming to UCLA, and maybe the quality of that was excellent and maybe it wasn't. So this is just to get everybody on the same page. So when we do hypothesis testing, we always start off with a null hypothesis, right? And the null hypothesis is that there is no significant difference between, you know, specified populations or any or that any observed difference that we see in our sample is due to sampling error or experimental error. Okay, so for example, you might have the question: is the I don't know, average rate of skin cancer different for men and women? Okay, maybe that's the question. And so your null hypothesis is that the two populations have the same rates of skin cancer, whatever it is that you are interested in. And then the alternative would be that they are different. Okay. Now, when you take your data, you're not going to get the exact same proportion for both groups. And so the question is the proportion difference between proportions, could that be attributed just to the random sampling, or is it an indication that the populations are different, right? So we always set that up. So the null hypothesis would be that there's no significant difference between the specified populations, and that any observed difference is due to sampling or experimental error. Okay. We also have to define something called the p-value. The p-value is the probability of obtaining a result equal to or more extreme or more unusual than what was actually observed when the null hypothesis is true. So if we assume that the null hypothesis is true, what's the probability of getting the data that we observed? And that probability is the p-value. Are we okay with this? Do we need a little bit more explanation here? Okay, so for example, we might have a hypothesis test where we are comparing the two means, okay, population 1 and population 2, and the null hypothesis is that their mean is the same. Okay, so maybe it's like you have lambs from farm 1 and lambs from farm 2, and I don't know, I'm making this up, right? And we're going to take a random sample of these things, and we say, you know, what's the average weight of the, you know, population 1 versus population 2. And when you take your random data, you collect data, you get x bar 1 is equal to 10 and x bar 2 is equal to 12. Okay? And the question is that difference significant, or could that difference of 2 be attributed just to random chance? Okay? And so, as always, the answer is it depends, right? And is the difference of 2 significant or not? That's going to depend on the standard error of our sampling distribution. What's the standard error? And not the formula for standard error, but what does the standard error mean? It's the standard deviation of the sampling distribution, right? Of the sampling distribution, right? And the sampling distribution is what? What is the sampling distribution? It's the distribution of possible sample statistics, right? So in our case, the sample statistic that we would be looking at is the quantity x bar 1 minus x bar 2, right? And the sampling distribution is what are all the possible different x bar 1 minus x bar 2 values that we could get. In our random sample, we got a difference of -2. If somebody else took a random sample from population 1 and population 2, they might get a different value, right? They might get 10.5 and 12.1, and that would be a difference of, I don't know, 1.6 or something, okay? So, you know, what are all the different possible values that we could get? That is going to be seen in the sampling distribution, and the standard deviation of the sampling distribution is the standard error. Okay, so anyway, here we have a difference of 2, and we want to know, is this significant? So in one scenario, the standard error could be very small, and the observed difference of 2 could be much larger, let's say 5 times bigger than the standard error, okay? And so in that case, we would say the difference of 2 is significant. On the other hand, maybe there's a lot of variation that exists in population 1 and population 2, and so the standard error is going to be large. So maybe the observed difference of 2 is not much larger, maybe only 1.2 times the standard error, or maybe it's even smaller than the standard error itself. And in that case, the difference is not going to be significant. And rather than just saying our observed difference is large or small compared to the standard error, we will use p-values, right? And all that does is it quantifies the probability of getting our data. Okay, so rather than just saying, hey, this one was 5 times bigger than the standard error, that seems large, and this one was only 1.2 times bigger than the standard error, that's not so big. We use that value, we look it up in a table or something, we get a p-value, and the p-value actually gives us a number. It gives us the probability of observing our data if we assume the null hypothesis is true. All right. So at the end of the day, if our p-value is tiny, that means the observed difference that we observed is so large, it is very, very, very unlikely to happen if the only source of variation is random chance. Okay, so if the only source of variation is random chance, it's very, very unlikely to get the result that we have, right? So if I'm flipping coins and I flip the coins 100 times, I would expect to get around 50 heads and 50 tails. If somehow I observed 99 heads and 1 tail, technically it's possible to get that from random chance alone, technically, right? But it's so incredibly unlikely, we would call that practically impossible. And so if somebody said they flipped the coin 100 times and they got 99 heads and 1 tail, you would be inclined to believe that they did something wrong, or they're not telling you the truth, or something is up and they did not get this result just from random chance. Okay? And that's the same idea with getting a tiny p-value. Tiny p-value means what happened is very, very, very unlikely to happen from random chance alone, and therefore we will come to the conclusion that it wasn't random chance alone. Okay? On the other hand, if the p-value is large, it means the thing that we observed in the data, that could have happened from random chance, right? Somebody flips a coin 100 times, they get 55 heads, all right? It's not exactly the same as 50 heads, but 55 heads is still quite likely to happen just from random chance. Okay, so in that case, the p-value is going to be fairly large, probably like 30% or something. And you'd say, all right, I'm going to believe you when you say it happened just from random chance. Okay. Okay. And that's what we did in intro stats, right? Stats 10. I'm hoping this feels reviewish, or at least jogs something in our memory regarding this. And all of those conclusions, right? When you looked up, when you did your t-test, or when you did a, proportion z-test or something like that, underneath all of that, there was some math underlying it, and that was the central limit there. And maybe you have to prove that in Stats 100b. Maybe, okay. And that shows, the central limit theorem says that the sampling distributions of the sample mean or sample proportion approach the normal distribution under certain conditions, okay? And you're supposed to check conditions to make sure that you can apply the central limit theorem. Okay, and that also sounds reasonable to you guys? Okay, and so we call these parametric hypothesis tests because when we think of what a normal distribution, how do we define a normal distribution? We define them with two parameters, the mean and the standard deviation. And so we call these parametric hypothesis tests. If we're going to take a computational approach to this, we're going to say, I don't want to deal with the math. I don't want to do central limit theorem. And instead, I'm going to be the source, or my computer will be the source of randomness. And we can simulate this idea of randomness, okay? So we can test the null hypothesis that there is no difference between group means. And we're not going to use the central limit theorem, but we're going to actually randomize our data, okay? And this is the key part here, okay? Randomization tests depend on this assumption of exchangeability, all right? And I'll explain what exchangeability is. Okay, all right, so let's, before we get into exchangeability, maybe we also have to do a little bit of review regarding data collection. So, what were the conditions that were necessary to use the central limit theorem? Okay, large sample size, and large sample size for proportions was that n times p has to be bigger than 10, and n times 1 minus p has to be bigger than 10, or that you have at least 10 successes, 10 failures. Okay, what else needs to be true? Constant variance is necessary. Equal variances to use a student's t-test, but you can have unequal variances if you use the adjusted one-Welch test. Okay, what about the way you acquired the data? Maybe it was too obvious. Like random sampling? Okay, yeah. So we need to get our data via random sampling, right? And our data need to be drawn independently, okay? And going along with the independent and random sampling assumption was that your population had to be big so that you're not sampling too much of the population, right? Or if you're going to sample too much of the population, you have to sample with replacement in order for your items to be independent. But anyway, okay. How we get the data matters, okay? And so here's just a silly scenario that we're going to just explore like 4 times in overkill and beating a dead horse, but here we'll do it anyway. Okay. So it says, suppose a dentist wants to know if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C. So this is the question that we're going to do. Okay. All right, scenario 1. So the dentist working through the local dental society convinces all of the dental patients in town with appointments in the first 2 weeks of December, so that will be next 2 weeks, to be the subjects of a study. He divides them into 2 groups, those who normally take 500 milligrams of vitamin C and those who do not. He asks them how often they have canker sores in their mouths and checks their dental records to see who has complained of canker sores. He compares the proportion of those who take vitamin C and have canker sores to the proportion of those who don't take vitamin C and have canker sores, okay? He does the math. He finds that there is a I have the written wrong. Okay, there is a significant difference in the two proportions, with a significantly smaller proportion of those taking vitamin C having canker sores. So he finds that those who take vitamin C, they have significantly fewer than those who didn't. Okay, so what can we conclude? All right, so first of all, what's the sample that we have? The sample is, how do we get our sample data? Yeah, appointments in the first 2 weeks in December to be subjects in the study. Okay, so then what would be the corresponding population? Yeah, okay, so, well, all right. Here's the problem. All right, the patients are not a random sample from any population, okay? Like, we got dental patients in town with appointments in the first 2 weeks in December. These, this is not a random sample. This is like somehow a convenience thing. Like, we're just going to go with the 2 weeks. And I don't know if there's any kind of correlation regarding what types of people schedule their appointments in the first 2 weeks of December, but these are people who, you know, make appointments with the dentist, right? And I don't know if that's every one of you, but, you know, if you didn't make appointments with the dentist, then you would not be included in the sample. So anyway, this is not a random sample, so therefore, any conclusions we make cannot be generalized to a population, right? So this is an important thing, is that if we want our conclusion to be generalized to a population, our sample needs to be randomly drawn from the population to which we are going to generalize. When we divide them into two groups, we did them in a non-intrusive way. We just said, who takes vitamin C? You do, and you don't. Okay, we're putting the people who do in this group and the people who don't in this group. So that's also an observational study. So we can't make any kind of cause and effect conclusions here, right? So all we can say is just that for these patients, so only for the patients who are in the study, those who took vitamin C have fewer canker sores than those who don't. We can't say why. We can't make a cause and effect conclusion. And we don't know if this result would be consistent with any other group. We can't generalize there. All right, let's change this up. So here we're still going to select those with appointments in the first 2 weeks of December, but now we are randomly assigning them, some to take vitamin C every day, and the other one are required to abstain from taking vitamin C. Okay, same results at the end of the study. What do we conclude this time? So what has changed? Do we have random sampling or no random sampling? No random sampling. Okay, what about random assignment? We do. So therefore, it has now become, at least we've done random assignment of the treatments, okay? So we still can't make any kind of conclusions that would generalize to a population. We still can't do that. However, the treatments were randomly assigned to the subjects. So the difference in proportions for having canker sores can be attributed to the different amounts of vitamin C, okay? Assuming the other stuff in this, okay? So all we can say is we don't know if this result would be consistent with another group, but we believe we know why for this group that the proportions differ. Okay, so with random assignment, we can make these cause and effect conclusions. All right, over here, we will have random sampling, okay? So we're going to take a random sample of dental patients in town, and we convince them all to be subjects in our study somehow, okay? All right, and then we don't do random assignment, so it's still observational, okay? Everything else is the same. So here, the patients were a random sample of dental patients in the town. So the conclusions that we make from the results of this study could be consistent with the result of the whole population of dental patients in town, okay? So we randomly sampled dental patients, therefore we can generalize to all the dental patients in town. Okay, I mean, that's not that exciting, but that's where we drew our sample, and so therefore we can only generalize to the population, right? We can't generalize it to everybody in town because you know, only certain people go to the dentist, right? So okay, again, it was observational, so we can't make any kind of conclusion regarding cause and effect. We don't know if there's some kind of confounding variable or something like that. Okay, and again, you know, we can't conclude for the general population since the sample is only of dental patients. So if the dental patients in this town, but if the dental patients in this town are representative of dental patients in general, we can infer that dental patients who take vitamin C tend to have fewer canker sores than those who didn't. Okay, so we can make that conclusion, but again, not anything about cause and effect. All we can say is that there's some kind of association here. Maybe there's a confounding variable, we don't know. Okay, and then lastly, if we do random sampling and random assignment, then we can generalize to the population, and we can make conclusions about cause and effect. Okay. It's easy to talk about this in a classroom setting and say, oh, here's a study where we had random sampling and random assignment. Okay. The truth is, in real life, we never get to do this. Okay. It's almost impossible to have truly random sampling. Okay. First of all, random sampling is like really, really, really hard to do. Okay. And then once you get random sampling, unless like 100% of the people that you've randomly selected, unless all of them 100% consent to be part of your experiment, it's not going to be random assignment either. Okay, because it's still not, if 100 people, like you randomly select people, that's a challenge in and of itself. But let's say you manage to do that. If 100 people don't consent, 100% of the people don't consent to participating, it's no longer a random sample because we don't know whether the person agrees to be part of the experiment or not is related to anything that you are studying. Okay, so especially if you're asking questions related to like privacy or you know, attitudes towards larger institutions and things like that, whether someone agrees to be part of your study or not will probably be related to the way they respond to these questions and whatnot. So so that's different. Okay, and then again, then you have to have a random experiment, a random assignment, and that's just really challenging to do. So I mean, in this scenario, it's nice. We say, oh yeah, we did random sampling and we did random treatment, and therefore we can make conclusions about cause and effect, and we can also generalize to the population. But generally, you do a medical study, it's certainly not a random sample. It's going to be like volunteers for the experiment, people who are willing to try on some experimental treatment for some disease or something. You know, that's not going to generalize to the population, and it might not even generalize to all people with that medical condition, because you have to think about who is going to volunteer to be part of a experimental study. It will probably be only those for which the traditionally existing methods of treatment have failed. Okay, and so therefore the effectiveness of this experimental treatment on this sample of people may or may not generalize to anything else. And so there's research is hard at the end of the day. Okay, research is hard, and getting truly good samples of data and doing truly good experiments is is challenging, right? So we often use animals that don't have rights, or we don't care about their rights, about consent and things like that, and we just say, well, you're a mouse, so we're gonna do this to you, and sorry. You know, I mean, but then, you know, they're mice, and so what happens to the mouse may or may not also happen to a human. But, you know, people have rights, and you can't just say, like, oh, we're going to do experiments on you because for the sake of science. You know, I mean, so, you know, there's a tons of questions, right? Like, if any of you ever become pregnant, or, you know, like you get married and your partner becomes pregnant or something, there's just a lot of questions. Like, we don't know, like, can you take this medication, or can you do this thing? And the answer, like, you try to do research and it's like, we don't know. And it's because you can't do experiments. So you can't be like, oh, well, in order to answer your question, we did experiments and we asked for a bunch of pregnant people to, and we said, hey, we're going to try out these drugs, and if they have negative side effects, we're sorry, but thank you for benefiting science. You know, that doesn't happen. So everything when you're pregnant is just like, I don't know, and maybe better not. So you just, anyway. Okay, anyway. All to say, we're talking about randomization tests. We're talking about this concept of exchangeability. And exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely, or that any other permutation of the data is exchangeable with other permutations of the data. Okay, that was like a mouthful. I don't even know if that makes any sense. What that basically means is that this concept of exchangeability applies to experiments where random assignment has been used. So if we use random assignment in the assignment of treatments, then it's feasible to say that, you know, if we had 50 people line up, and for every person we flipped a coin and we said, if it's heads, you're in group A, and if it's tails, you're in group B, you know, then we can imagine for the 50 people who lined up, we could have, if we flipped another series of coins, we could have gotten some other split of the groups, and every single possible permutation or every single possible split or rearrangement of those treatments are equally likely. Okay, so that's what we have with exchangeability. So if the patients are assigned treatments randomly, any arrangement of patients is equally likely. All right, and if we're not doing coin flips, then you could think of maybe we had 50 people lined up, and we said the first 25 are going to be in group A, and the last 25 are going to be group B. But then those 50 people could be, you know, shuffled around, and the order of those 50 people could change, and any other possible permutation or ordering of those 50 people are all equally likely. So that's what we have here. Okay. So if we did an observational study, exchangeability does not apply, okay? Because we did not do random assignment, and so different permutations of the group are not going to be equally likely. Okay, so this is the key part here. If we're going to do a randomization test, you can only do it if the data that you are going to kind of reanalyze with a randomization test had used random assignment for the treatments. Okay, let's watch this